Welcome back to Project Methania. In the last episode, we explored how life emerged, developed complex biological pathways, and eventually built the first multicellular organisms. As promised, in this episode, we will see how life will take its first steps on land. But as many of you asked to explore more aquatic niches, we will do it as well. So, let's start. We ended up with a simple ecosystem that can be found in shallow waters of Methania. But as time passed on, many species spread to other regions. A group of plants called Fluminitosa might spread to colder parts of Methania that are closer to the poles. In regions like this, a process known as upwelling occurs more often. It is signified by the rising of deep, cold, and nutrient-rich water to the surface, which is mostly driven by wind patterns. This process enhances the nutrient availability in these regions, which will allow Fluminitosa to grow taller than their shallow water ancestors, reaching up to 40 meters in length. The upwelling is also responsible for much stronger currents. To avoid damage caused by it, their leaves will evolve to be thinner and their roots will develop more branching structures, providing them with better grip to the ground. Eventually, followed by plants, many herbivorous species will migrate to these regions as well. A group of pentacrabs called Aquila pentacrabs will be one of the first groups to start living here. Compared to the shallow waters they originated from, this biome will feature a more complex habitat structure due to dense growth of Fluminitosa. Navigating this environment will be somewhat challenging, but will offer numerous hiding spots. Since the leaves of Fluminitosa only begin to grow at certain height, Aquila pentacrabs will evolve to climb the stems of these plants to reach the nutrient-rich leaves. Their limbs will grow longer and become more muscular to help with this adaptation. Their eyes will eventually move to the sides of their bodies instead of the bottom, providing them with a better field of view to navigate more efficiently in this complex environment. And their mouth will develop two round plates that will be used for cutting the leaves of Fluminitosa, but also scraping small algae off stones. In shallow waters, the main predators of pentacrabs were Tentaculumors, so they might follow them to their new habitat and adapt to it as well. Originally, they adapted their bodies for better maneuverability rather than speed. However, in regions with stronger currents, a more streamlined body plan will benefit them more. Their mouth appendages, as well as eye stalks, will become more compact, and their overall body shape more streamlined. Their fins will undergo similar changes. On Earth, fish that live in environments with weaker currents evolve to have more round-shaped fins, where fish that need to move through stronger currents evolve to have more sharp and streamlined fins. Tentaculumors that migrated to these regions might experience the same, making them faster and more agile compared to the shallow water relatives. In shallow waters, Tentaculumors preyed on slow pentacrabs by simply flipping them with their tentacles, but with more agile Aquila pentacrabs, they will need to find another way of preying on them. They might develop their second pair of tentacles into strong pincers, allowing them to crack the tough shells of Aquila pentacrabs. Let's call this group Osfractans. One of the first multicellular species was Radicis tumulus, a relatively simple organism that primarily fed on bacterial mats. However, over millions of years, this food source has become increasingly scarce, due to species of Glomerulithosa gradually transforming hard mat grounds into softer sediment by burrowing with their anchoring structures, creating air pockets and eliminating the hard surface where bacteria thrive. In response to these changes, a small group of Radicis tumulus, through a process known as neoteny, may develop an organ to filter water for nutrients by adapting their porous room that they have in their larval stage as a filtering area similar to that of sponges found on Earth. Eventually, to maximize their efficiency, they will develop an osculum that will help them with expelling already filtered water. Let's call this group Porotumulus. This adaptation not only allowed them to survive during the early Clethromethanian agronomic revolution, but also allowed them to spread to more regions, including deeper waters of Methania. To thrive in this hostile environment, they will need to address problems such as high pressure and lack of sunlight. On Earth, deep-sea sponges were often found with the strongest supportive structures compared to their reef relatives. It was often made of silica and allowed them to withstand high pressure of deeper regions. On Methania, however, silica will not be as commonly found as on Earth. since it requires oxygen to form. Instead, Methania's methane-rich atmosphere will provide the deeper parts of the ocean with more methane clathrate, also known as hydromethane. It forms when hydrogen-bonded water and methane come into contact at high pressure and low temperatures. A group called Abyssapora will evolve to use methane clathrate as their main component of their structural support. Not only that, but because of deep-sea pitch dark conditions, they will most likely lose all methanosynthetic cells, and with them, their color. However, they won't be the only species whose relatives evolved to live in deeper regions. In lower parts of the epipelagic zone, a group of Glimmerithzosa, called Florithosa, will evolve a way to spend part of their life in the regions with very little sunlight. Right after being born, they will attach to the rocks or substrate by using their newly evolved root system that will provide them with much stronger grip compared to the roots of their relatives. As you might remember, plants on Methania don't engage in photosynthesis, but use methanosynthesis, which produces hydrogen instead of oxygen. This group, instead of only storing small parts of this hydrogen to provide structural support, will evolve much bigger porous rooms to store as much hydrogen as they can. By doing that, they will provide themselves with stronger uplifting power that will elevate themselves along with the substrate they are growing on, providing them with more and more sunlight, thus creating a new type of underwater biome called floating islands. For pentacrabs, this biome will be too risky to navigate, since in case of falling from the island, they might fall in much deeper parts of the ocean, with lower temperatures and higher pressure, so they won't migrate to this biome. On the other hand, actively swimming tentaclemores will have less problems navigating through the floating islands. The structure of this biome will be more complex compared to shallow waters, but by being located closer to the equator, will have much bigger current. So for tentaclemores that evolve to live here, an even more maneuverable way of swimming and a bluff body shape will be more beneficial. Along with that, two back pairs of their fins will be reduced to small spike-like appendages that will be used as mechanoreceptors and protection against rare predators that venture to this biome. The front two pairs will be used for locomotion. To gain more energy from Florithosa, they will need to change their diet. As it can be seen on Earth, when carnivorous species venture to new habitats where prey is scarce, they typically adopt a more herbivorous diet. This process is usually referred to as dietary shift and can be observed along many clades on Earth, with most known examples being giant pandas and bees. Due to Flareithox being mostly hydrogen-filled, eating them will not provide these tentaclemores with many calories, and eventually they will need to get smaller. Let's call this group Agilepiscis. As well as being herbivores of floating islands, they will also protect them from other less buoyant plants by simply eating them, allowing for more healthy development of the floating islands to take place. As mentioned before, most of the Radicis tumulus species evolved to fill the niche of sessile filter feeders. But one particular group will explore a new niche that will completely change the history of Methania. During late Methanian, land will be a very unwelcoming place, mostly made of bare rocks and sediment where most plants will have hard time growing and animals simply die of starvation. But a group of extremophiles called Radicis Amara will be the first organisms to colonize this terrestrial environment. Originating in the intertidal zone, they will develop a strong root system that helps them withstand the force of strong waves near the coast and prevent them from being washed away. But to go further, they will need to find a way to grow on more hard substrate. Similarly to early terrestrial fungi and today existing Aspergillus species, they might start producing strong acid to dissolve rocks, which also will give them access to minerals that are required for healthy growth, such as copper, phosphorus, magnesium, and many others. For this purpose, they will use oxalic acid that will be produced by a group of specialized cells with modified pathways of hydrogenic fermentation, where breakdown of vinegar leads to production of oxalic acid and methane instead of methane and water. Later, this acid will be distributed to the roots of Radicis Amara, turning hard rock into first soil. Additionally, they will need to develop a new method of reproduction. Before moving onto land, their ancestors relied primarily on water currents to disperse their male gametes. However, on land, there are obviously no water currents, necessitating the development of a new organ to facilitate this process. This organ will function similarly to squirting cucumber fruits, building up pressure in lower chambers and releasing the gametes under optimal conditions, thereby increasing the dispersal area. With Radicis Amara now successfully reproducing, thriving on land, and contributing to the creation of richer, more fertile soil, other organisms can now begin to colonize the land. Utilizing the nutrients and support from this newly formed fertile soil, plants will begin to colonize land. One of the first plants will be Glimmeritosa, that will begin to grow in shallow waters with moist air and weaker currents. Their long roots, formerly used for digging into the ground, will become much shorter and more branching, so they could have a better grip over the soft dirt. To prevent water loss, they will develop a waxy layer on the surface of their leaves, known as cuticle. Although it will solve the water loss problem, it will complicate the uptake of gases that are needed for methanosynthesis, leading to less glucose production. To address this problem, they may develop a structure called stomata, which will open to intake methane and close to prevent the water loss. These stomata will be connected to the phloem to ensure the transportation of the gases in the plant. With this adaptation, a race will start. Taller plants will get more sunlight, and smaller plants will get less, driving plants to grow taller and taller. Eventually, a group called Herbithosa will reach a form that we will classify as a tree. While most tree trunks on Earth develop fibrous tissues made of hard materials to support their canopy, trees on Methania won't need it, as their hydrogen-filled leaves are already providing enough uplifting power to support themselves. Instead of that, trunks of Herbithosa will be more spongy and gelatinous, offering greater flexibility, enhanced nutrient storage, and faster recovery. Similarly to Radicis Amara, they will develop an organ that will allow them to spread their male gametes more efficiently. But along with that, in more complex plants like Herbithosa, some of them will also develop an organ that will be only found among female species, consisting of a chamber where their larvae will develop. With the introduction of additional plant biomass, Radicis Amara will have the opportunity to grow taller. Unlike plants, however, this growth will be driven by force, resulting in taller Radicis Amara species exhibiting a wider spread of gametes. This newly formed group called Radicis Amara peralta will reach up to 3 meters in height. Now that the land is colonized by plants that are able to provide nutrients, it's time for animals to do their first steps on land. A group of pentacrabs that were primarily attracted by plant matter that was washed up on coastlines will become one of the first species that will start to spend the majority of their life on land. To do this, they will need to change many things in their morphology. Their crab-like gills, that mostly relied on water flow, will not be efficient enough to live on land, so they will need to change them. The overall shape of their gills will become more wing-like and folding in several places, providing them with bigger surface area for gas exchange. Pentacrabs will also develop mucus-producing cells to ensure that their gills won't dry out. Since they will rely on passive form of breathing, their size will depend on how high is the percentage of hydrogen in the atmosphere, allowing them to reach only 5 centimeters in length. With now being able to breathe on land, they will develop bodies that are more suitable for locomotion in their new environment. Longer limbs will allow them to move faster compared to their marine relatives, and in some cases allow them to climb on tall herbithogs. Although having longer limbs will provide them with many benefits, supporting them solely by using muscles will not be very energy efficient. Their ancestors had a chitin-based shell that was mostly used as a way to protect themselves from predators. But as they move on land, the same shell might serve as a supportive structure. It will extend onto limbs and the bottom part of their body, allowing them to grow up to 10 centimeters in length. This structure, known as exoskeleton, will also prevent them from losing water through their skin. Let's call this group Pentacrab arboricolous. Their diet will include plants and plant matter that was washed up on the coastlines. However, due to high acidity of Radicis Amara and Radicis Amara peralta, they will not be a viable food source. But pentacrabs will not be the only animals to venture on land. A group of carnivorous tentaculumors might eventually start migrating into swampy environments, where they will be able to hunt or scavenge on dead pentacrabs. In shallow regions, while moving underwater, they will often need to push themselves up by using their fins, which will lead to the development of stronger, more specialized limbs, that can support their weight and help them navigating both in aquatic and terrestrial environments. However, the last pair of limbs that was mostly used for steering while moving underwater will eventually be reduced to a pair of flaps that will be used for thermoregulation. To enhance their grip on the soft ground, their limbs will develop two finger-like appendages. To stay hydrated and lose less water, their skin will thicken and their shell will become larger, acting as a reflective surface that helps reflect sunlight, thereby reducing the amount of heat their body absorbs. Similarly to pentacrabs, they will need to deal with respiration that can no longer be supported by water currents. Luckily, the ancestors of these terrestrial tentaculomores had stronger muscle rings that allowed them to close and open the entrance and the exit of their respiratory system, which was used to create force that allowed them to use jet propulsion. These muscles will not only allow them to pump hydrogen-rich air inside of their canals, but also hold it inside by sealing off the openings, thereby preventing the air from escaping permanently, allowing them to extract more hydrogen from it. Additionally to that, canals will thicken in the middle, providing even more space for the air, where newly developed bronchi-like structures will increase the surface area of the lungs. Overall, their gas exchange process can be divided into three stages: intake of air through the front openings, closage of entry and exit followed by gas exchange inside of the lungs, and finally release of the air through the back openings. This newly developed group will be called Tentatestudo, and their arrival on land will symbolize the new era. Welcome to Early Remarian. Thanks everyone for watching, and for all who submitted their art for this episode. If you want to see more, make sure to like and subscribe. We also have a Discord server, where you can submit your art for the next episode, stay updated on the project, and just be a part of the community. Until next time, and remember, never stop exploring.